So we are continuing from module 4, question 2. Okay, so remember that this is from module 4. Okay, so my marker is off, so let me bring it back. Okay, so module 4 was where we left off from. Okay, so we will continue from there and then see how far we can go. Okay, so from there, recall that we were discussing already some questions on that module, and we before when we left. Okay, so let's see. That should be page 35 or thereabouts. Page 35, if I am correct. Okay. Page 30, 32, 31. Yeah. Page 30. Okay. So question 2 says, the A part says find AI self. This is serious. So it's AI. So it says find a basis and dimension for the subspace H. So you can see that all what we've been doing for the past 1-2 modules are about basis and dimension of vector spaces. So it's more of vector spaces. Okay, for the subspace, and the subspace there is H of R3, okay, spanned by the vector, spanned by the vectors. Okay, so here are the vectors: v1 equal to 2 minus 8, 6, then v2 equal to 3 minus 7 minus 1, and then v3 equal to minus 1, 6, and minus 7. Okay, so we should find the vector space, subspace, that is spanned, the basis and dimension for this subspace spanned by this particular one. Okay, so what is that? All we need to do is put this in matrix form. So we start and then reduce it to echelon form. That will give us a hint. Okay, so we will let our A, of course, be the matrix of these 3. So let A be equal to you have, okay, of course, this is going to be 2 minus 8, then 6, and then this one will be 3 minus 7 and minus 1. Of course, they will be in the form of a column matrix, and then this one will be minus 7. So you will now they will form the columns of the matrix. Then you will now transform. Okay, so the transformation is just to get a row reduction, and then if after row reducing, any row that disappears will now tell you what your bases are. Okay, so let's look at it. So this row reduction is going to give us something like, of course, remember that this is 6, not minus 6. Okay, so this one is 6. Now, okay, so we can write the algorithm. Of course, we want to first of all make these 2 zeros. So equation 1 remains unchanged. Okay, so now to change this, we are going to, let's try to formulate what the algorithm will look like. So we can have, we are changing R2 to, okay, your R2, the signs are different, so we can use plus. So if 4 multiplies this, that will be 8, so the addition will give us 0, so it should be 4R1. Why this one? The signs are the same. Remember, your pivot is this one, so you have R3. Since the signs are the same, you subtract, so 3 times this will give us 6, so we have 3R1. So let's apply this. Okay, so if we apply it here, we have 0, and if we apply it here, 4 times this is 12, so we have minus 7 plus 12, and that is 5. And then we come over to the last one, 6 plus 4 times this is minus 4, so you have 6 minus 4, which is 2. Okay, so then you are done with that row. So we come over to the last row. Of course, this first one will be 0. Second one is minus 1 minus 3 times this will be minus 9, so we have minus 10. Okay, and then this last one, we have minus 7 minus 3 times this will be plus 3. Okay, and if you add this, you will have minus 4. Okay, and then of course, if you divide this by 2, you will see that it's going to give you exactly what you have here, but in the negative direction. So which means that this is just a multiple of this, and so by the time, since it's a multiple, so you just have only 2 linearly independent sets here. So, and that is going to produce the basis that you're looking for. So, but in completing that, we are going to be eliminating equation 3 again. So, sorry, replacing it. Okay, so let's try to replace it. That means our equation 1 and the equation 2 will be the same, 0, 5, 2. Okay, so what's our equation 3 now? So just do R3, the signs are opposite, so we'll add R3 plus 2 times this will be 10, so you have 2R2, and so you have 0, 0, and then this one will also be equal to 0. All right, so that means that you can see our reduction, what it gave to us. Okay, so and so from there you can see that the first 2 columns are pivots. So because we are getting pivots, let me use this, we are getting pivots from the first 2 columns. So the ones that are able to give you pivots are the vectors that are that will form the basis. Remember, we are looking for the basis. So there, what it means therefore is that the basis for that particular subspace is going to be the first 2 vectors, because they are the ones that finally had pivots at the end of your echelon reduction. So this is going to be vector 2 minus 8, 2 minus 8, 6. That's, you know, this is the first vector, and then vector 3 minus 7, 1. Okay, so, and which are your V1 and V2. So that will form the basis. Let me call it I, and then I, okay, anyway, we already have I, so let me not give it any name. So then the next question say dimension. So the dimension of that subspace H, I think that's the name they gave to us. Let's see. Okay, yeah, subspace H. Okay, the dimension is going to be equal to 2, because the number of vectors in your basis is 2. Okay, and you are done. Okay, so we move over to the next one, which is II. So in II, we are told that our V1 and V2, V3, all members of the basis. Okay, so II is just even responding to the questions that we are asked. Are they members of the basis? No. Okay, if no, then present that non-member as a linear combination of the members of the basis. Okay, so like I said, that you can even see it from here, that this okay, All right, let's see. So they are asking us to present this as a linear combination of the bases. Okay, so let's try to do that. Since it's not a member, it means that it must be a linear combination of the other two. And the one that is not a member is, look at it here, that's the third vector, v3, which is minus 1, 6, and 7. So we want to present this as a linear combination of the other two. Okay. And then, of course, you can do that by trial and error. So let me write the other two. Look at them here. 2 minus 8, 6. Because of your time, you can try that by trial and error. Just put addition here for the sake of it, but it can be minus. So this will be 3 minus 7. This will be 3 minus 7. And then we have okay, excuse me. Okay, so 3 minus 3 minus 7 and minus 1. Okay, so that's what we have. Okay, so what do you have here now? So you can see that from this point now, I can try to do some trial and error approach. Sorry about that distraction a little bit. So you will try to see how can I combine these two things to give me this other one. All right, you can attempt. Okay, trial and error may be a little bit difficult. So what you will do is, let's just fix constants here. So fix x1 here and x2. Okay, so you are looking for x1 and x2 that will be equal to this. So, and that will lead you to systems of equations which you will solve. But then you can actually get this from this row reduction that we did here. I think so, yes. Yeah, from the row reduction that we did here, that's the same thing that we would have done in that place. So all you need to do now is to now draw, so you are now equating the third vector as the vector on your right hand side. So you are going to have, so this is now going to be your constants. You are no longer seeing them as vectors, so they are now constants, because that's what you want to get here. Look at it here. So you want this to be equal to this, and you're looking for the x values that will do that. So you just have only x1 and x2, which are here, and then this other side will now be your constant, which is what we got from this point. So that's actually what we are doing now. So this side is now our constant. So all you need to do here now is to now equate this into 5x2 is equal to 2. So that will give you your x2 as 2 over 5. This is beautiful. And then make this other equation to now become 2x1 plus 3x2 is equal to minus 1. So you substitute what is our x2. Our x2 is 5 over 2. So if you multiply, you will get 6. You get 6 over 5 equal to minus 1. So that means 2x1 is equal to, this coming over here will be minus 1 minus 6 over 1. So if you change this to LCM, you have minus 5 minus 6, which will give you minus 11 over 5. So we have minus 11 over 5 here, and then divide both sides by 2. You will get that x1 alone is minus 11 all over 10. Okay, so we have gotten x1 and x2, and that means that is the value of our x. And you can check it. You can check it that it is true. If you put x1 here as minus 11 over 10, and then you have 2 minus 8 and 6, and then put x2 as, I think I got 5 over 2. Yeah, I got 5 over 2. So if you put 5 over 2, or was it 2 over 5? Sorry, let me be sure. X2, yeah, 2 over 5. Sorry about that. Okay, so if you put this as 2 over 5, so you will have that multiplying 3 minus 1 and minus 7 minus 1. So is this going to give us this? Let's check that. Okay, let me quickly run that here. So you see that this times this will give us minus 11 over 5. This times this will give us is it? Yeah. Then this times this will give us my 44 over 5, because 8 will cancel. This will give 4, and 4 times 11 is 44, and that's minus 4 times minus 11 is 44, then over 5. And then this one will give 11. Okay, this will give 3, that's minus 33 all over 5 also. Okay, and then that is plus on this side you will have this times this is 6 over 5, this times this is minus 14 over 5, and this times this will give you minus 2 over 5. Remember, I'm just trying to run a check for you to be sure that it's equal to what we have there. Or let me just reduce this. Yeah, okay, so this I want to now add this. So this is going to be of course the bases are the same, you just be adding, the denominators are the same, you just be adding the powers. Minus 11 plus 6 will be minus 5 over 5, and that's minus 1, which is already this. Then this one plus this, 44 minus 14 is 30 over 5, which is 6. Then minus 33 minus 2 is minus 35, and minus 35 over 5 is minus 7, and that's exactly what you have here. So that means we have expressed V3 as minus 11 all over 10 V1, then plus 2 over 5 V2. Okay, and that means we have expressed V3 as a linear combination of V1 and V2. Okay, so in other words, if you want to write, you don't need to write everything here, just write this as this because of your space, and then when you do that, then you will now just pick, you come up and then finish up this solution. Maybe somewhere you can just save from this equation, you get that x1 and x2 is equal to this and that. Then you substitute it here as your solution so that it will enter into the little space that you have. Okay, so and that is for II. Okay, and then III, we are still in A now, I think so. Yeah, 2AI and then II. So we go to III, which is in page 32. Okay, so and that one says that we should write down 2 non-zero vectors of column A. Sorry, 2 non-zero vectors in column of A. Okay, all right, sorry, it seems I jumped. Okay, sorry, I went down. Okay, so it says okay, I says are V1, V2, V3 linearly dependent or independent vectors. Okay, so of course we just express one as a linear combination of the other. So it means that v1, v2, and v3 are linearly dependent. So since one is a linear combination of the other two, so but if you remove v3, then only v1 and v2 are linearly independent, and that's why they formed the basis. Okay, so you say we should give reason. The reason is because let me use because we just expressed, because v3 is expressible as a linear combination. I just said that because v3 can be expressed as a linear combination of v1 and v2, and you can also write it for them where that linear combination we got already as minus 11 over 10 v1 plus 2 over 5 v2. Okay, so that's enough reason to confirm that they are linearly dependent. Okay, and that's I so we go over to B now, because that's the last question for A. So B says you are given that A is equal to, given that A is equal to 2, 4, then minus 2, 1, and then you have minus 2, minus 5, 7, 3, and then you have 3, 7, minus 8, 6. Okay, is your A, and your U is equal to 2, 3, minus 2, minus 1, 0. Okay, and V is given as 3, minus 1, and 3. Okay, so the question says that's our V and U. Okay, so it says I that we should let me take up a little. Okay, so I says that we should find what if the column space of A is a subspace of Rk, then K is what? Okay, okay, column space of A. So all you need to do here is when we're talking about column space, so we're talking about the subspace, or I can just call it a vector space that is formed from the columns of a matrix. And for you to get the column space, you would have to reduce this to echelon form, and then just like what we did in question A above, you will try to determine the basis. So you will remove the ones that are linearly dependent to the other, so the remaining will give you the column space. Okay, so that means we would need to that means the ones that will have pivots will be the ones that will give you the column space. So we need to reduce this to echelon form. Okay, let's try. So we'll have 2, 4, minus 2, 1, then minus 2, minus 5, 7, and 3, and then you have 3, 7, minus 8, and 6. Excuse us. Okay, so this is equal to, all right, in reducing this, our row 1 will remain the same. So we have 2, 4, minus 2, 1. Okay, sorry, not minus 1, minus 2, 1. Then row 2 will change, row 3 will change. So what will be our new row 2? Just eliminate these 2. Okay, and to do that, you just add, because the magnitudes are the same, just negative. So here we have if you add, you get 0. If you add this one, you get minus 1. You add this one, you get 5. You add the other one, you get 4. Then what about row 3? Row 3, both of them are positive, So we are going to subtract, but we will need to multiply both rows. So I need to exchange the coefficients. So 2 here and then minus 3 here. Okay, so let's go. If you do that, this one will turn to 0. If you do that here, you have 2 here is 14 minus 3 here is 12. You get 2. Then coming over here, you have 2 into minus 8 is minus 16. Then minus 3 times this is plus 6. Then you have minus 10 here. And then here you have 6 times 2 is 12. And then minus 3 times this is minus 3. So you have 9 left here. Okay, so what is going to happen now? So we are done with that reduction. We are done with that reduction. So we are going to be going to the next phase of the reduction, and that is going to be to now change this 1 to 0 as well. Okay, so and that means row 1 and row 2 will remain the same. So in row 1 we will have minus 4 1, and then here you will have 0 minus 1 5 and 4, and then here you will have, okay, what will be the algorithm? So here we want here to be 0, using this as a pivot. So you discover that we can use R3 and then multiply this by 2. Since the signs are the opposite, you add. So this is going to be 2R2. Okay, so and in doing that, we will get, of course, 0 0. Then this one, R3, 2 times this is 10. If you add, you will also get 0 here. And then this last one, you've got 9 plus this times this is 2 times this is 8. So you get 17 here. All right, and you are done. So if you come back here, you discover that column 1 has a pivot, column 2 has a pivot, but column 3 has no pivot. Okay, so that means column 3 is not that means vector 3 is not linearly dependent with that, but this one now has a pivot. So if we interchange this, then you can see there is a pivot here, and so that means your what do you call it, your column space will only contain the first vector, second vector, and the last vector. Okay, so it will contain the first, second, and the last vector. Okay, so that means that it is going to be, let me come back to the place where we started. Okay, yeah. Okay, so that means that remember they said for I that we should put A in a column space and then get the dimension. And so, and we got that our R now has only 3 vectors. So what that means is that our K is equal to 3. Okay, and then the second part, which is II, now says that we should, if the row space of A is a subspace of RT, then T is equal to what? Okay, so here they are now asking for the row space of the same A. So if it is RT, so what is T? Meaning they are asking you for the dimension of the row space. Okay, so what would that dimension give us? Okay, so you can see here now for the dimension, you're also going to look at this. So, and if you look at this place, you are going to see that so you are going to see that, of course, if you interchange these two, this is still going to be something of this nature. Look at it. It will be like this: 2 4 minus 2 1, and then 0 minus, sorry, I want to interchange these two, so I'm going to be having where is it? I'm going to be having minus 1 I'm going to be having 1, 4, 17 here. Then I will have minus 2, 5, and 0 here. Then this one will be 0, 0. Okay. So assume that you have something like this. Did it lead us anywhere? No. Okay, no, it didn't. All right, so return back to where we were. Okay, so for our row space, you are going to see, of course, that this one now, the row space is now going to be all of these. That's this one too. But here now, what can you say about here? You can say there is no pivot here, so we'll also eliminate this from the row space. So the row space is only going to have only 2 vectors. So in that case, what you have there is that your row space is going to be RT, which is equal to R2. And so if that happens, then your T is equal to 2. Okay, so having done that, now the III says that we should write down two non-zero row vectors of A. 2 non-zero row vectors of A. Okay, let's come back to our A. This is our A here. Okay, so the 2 non-zero vectors of A includes, of course, you have this and this. Okay, so we can write that. So that's going to give us. Okay, now meanwhile, come back here so that, okay, sorry, look at this. Sorry, I just made a little mistake here. See that, look at what we have here. Now, you know that, hey, Jesus, Miss Summer, don't come in here again, no. So you can see that the row vectors, like I told you, are going to be, now meanwhile, even this is going to be part of the row vectors. So it's going to be, sorry, I eliminated this. So this is going to be, you have, did I need to eliminate that? I'm not going to eliminate because it also has a value. So it's only this one in terms of column space that you will eliminate. So here you are now going, sorry about that. So here you are going to have, now look at how the vectors will be. Let me assume that the column row vectors are represented as R1. So the first R1 is going to be 2, 4, minus 2, and 1. And you can see it contains 4 components. So it's actually R4. It's actually R4. So which means that our T is equal to 4. Is actually equal to 4, and so not equal to 2. Sorry about that. Okay, so now, and for the column matrices is actually supposed to be 3. And why is it 3? Is because if you pick all the elements of this, you are going to have all the elements of the column matrices or the column space will be of 3 components. So this will be 1, 2, 3, 1, 2, 3, and so on. Okay, sorry about that. That's why K is 3 and that's why T is 4. So but they now said we should bring out our any 2 row matrices that are non-zero. So I've already brought out one, so we can call it R1, and our R1 is equal to, I said, 2, 4, minus 2, and 1. And then we can have R2, and our R2 can be the second row there. The second row there is 0, minus 1, 5, and 4. Okay, so this can be 2 non-zero. You can even pick the last one, is still non-zero, because at least there is one element there that is not a 0. Okay, so and that is for III. Okay, so we go over to IV. So the IV says that write down two non-zero vectors in the column vectors. I just mentioned that now. So just pick out some of the column vectors. So you can pick out this one, or this, any of that. Okay, so you have 2 0 0. So let me call it C1 as column vectors. You have 2 0 0. You have maybe C2. You can have, what do I have there? 4 minus 1 0. 4 minus 1 0. Okay, and then the other one is you can even pick the other one where there is no pivot actually. All right, it's still a column vector. That's minus 2 5, or you can pick 1 4 and 17. Okay, any one of your choice. So you can have C3 1 4 17. All right, so all right, and that gives us all the examples. You can pick the other one too, like I said. So there are about 4 column vectors there, and so that's that for IV. And then for the other one is a bit blurry. So it says determine if U is in column A. Okay, sorry, in col A. That means in column space of A. In other words, is it possible to get something? I'm going to V now. So determine if U is in column A. So what you're trying to do is let me see. Okay, okay, so meanwhile, you see I'm picking the reduced matrices. Sorry, the reduced this thing. You can actually pick from the main matrix actually. That's for where they are asking for vectors in column A and in row A. You can pick this one that is originally given in A. So you can pick this as a row matrix, row vector, and you can pick this column vector, and all of that. I picked from the reduced one, so you can pick from the original matrices. That won't be bad. Okay, so let's get back to where I was. Okay, so to determine if any is in where is it again? If U is in null A. Okay, so that means okay, I even jumped that one. To determine if it's in null A is to show where is our U. Our U, let's recall U. Our U is given as minus 3, sorry, is given as 3, minus 2, minus 1, and 0. Okay, so they are asking us to determine if it is in the null of A. And so all that is saying is if that we should check if you multiply. So that means we want to check if A times that U is going to be equal to 0. And if you check it, what is our A? Bring down our A. You have 2. You can do all of this on a rough if it doesn't enter the space that you are given. Okay, and then you just bring in the conclusion here. So if you do 2 4 minus 2 1, then minus 2 5 minus 5, then 7 3, and then you do 3 7 minus 8, and then 6, and then you multiply it by your U, which is 3 minus 2 minus 1 and 0. You are going to have something of this nature. This times this is equal to 6 minus 8. This times this is plus 2 and then 0. I think we have done something like this before. This one times this is minus 6. This times this is 10. I think we have done this before. 7 times this is minus 7, and then this times this is 0. Okay, so plus 0. Right now the next one is this times this is 9, and then we got minus 14, and then we have plus 8, and finally we've got 0. So if you couple what we have there, you will see that, let me go this way instead. So you will see that our a times u is equal to, this one actually gave us 0, but this one didn't give 0. I think this one gave -3, and then this one gave 3. Yes, okay. So you will see that since this, so this is the conclusion you can bring for us. So if there is no space to solve this, so you can just say, even from here, since our a times u is equal to, you can just bring what you got there, 0 minus 3, which is not equal to 0. Therefore, you can conclude that u is not in the null space, is not in the null space of A. Alright, so u is not in null A. Alright, that is enough. Okay, so we now move over to the next one. Determine if u is in the column space of A. Alright, so what do you need to do there? So to determine if u is in the column space of A is to check, of course they gave you a hint there, to check if A times X is equal to your u. Okay, that means if you can find any X value so that when you multiply with A, you are going to get u. Alright, so I'm going to be pausing here, and then I will continue from this particular VI in the next section, and then we'll finish up. Alright, so have a very nice day.